Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
John Rogers is here from UIUC. He does nano and molecular scale fabrication, materials, patterning, and builds some really crazy electronics, as you'll see today. He's got a chemistry physics background, and in fact has a physical chemistry PhD out of MIT. He spent time at Harvard, Bell Labs, where he was in the condensed matter physics department, and in fact ran the department for a number of years. Is now the Swanland Material Science, or Swanland Chair in the Material Science and Engineering Department at UIUC, with joint appointments across just about every department you can imagine, and so I'm not going to list them. His publication patent, press awards list is massive, and again, you can look at his bio for a small snippet of that. He's also had multiple startups, starting with his PhD work, and I guess recently with a company called MC10. Which I don't know if you're going to talk about.
A little bit, yeah.
But if you look at his project list as well, he's done everything from stretchable lithium-ion batteries and silicon ICs to flexible silicon photovoltaics, electronics on balloons for surgical catheters, cellular scale optoelectronics, negative index metamaterials. The list goes on and on. The thing he's going to talk to us about today is in the biointegrated electronics space, specifically epidermal electronics. So rather than get in the way of a great talk, I'm going to hand it over to John.
Okay, all right. Hey, thanks a lot, Desney, for that introduction and for the invitation to come here and spend some time at the labs. It's bringing a lot of good memories back from my time at Bell Labs, sort of, a research lab in a company that makes products. And so I think it's a great environment to do innovation. I'll tell you about some of the things that we've been doing at Illinois recently that may be of interest to hardware interfaces to the body, of relevance to future computing and health and wellness and sports and other things. And it's referred to, this is a term we made up, sort of epidermal, in the sense that the electronics themselves have physical properties pretty well matched to the epidermis, so they go on in a way that's more or less invisible to the person wearing the devices, which we think is important for kind of an intimate, high functionality interface to the body to have that kind of wearability. So I'll start by giving you a motivation, what we're trying to do, perspective on how this kind of electronics relates to more conventional stuff. I'll give you some ideas around requirements in materials and mechanics and manufacturing in order to do this kind of skin integration. And then the last half, maybe the last third or so, is just step you through a bunch of examples of things that we've built with the idea that this is still in the early days, and I think there are a lot of opportunities for new ideas and higher levels of functionality, but just give you a snapshot of where we are right now in the development of this kind of technology. So let me just start by telling you something that is obvious. You already know it, but it's a useful reference point, which is the future of electronics, where it's been in the past, where it is now, and where it's going into the future. And it's really all about making things smaller, faster, and cheaper. So in the old days, you have giant boxes that fill desktops or fill rooms. They're used primarily for specialized industrial, academic computation, but Moore's law, miniaturization in the transistor sizes, reduction in their cost, increasing levels of functionality, really transformed the hardware into completely new device formats. And that's an engineering accomplishment. Maybe the more significant one is it introduced a qualitative shift in the way that computing devices are used in our everyday lives. Much more ubiquitous, much more personal as communication tools, productivity enhancement systems, and entertainment devices. And if this is where we were, this is where we are, where we go in the future, it's a pretty easy answer. You just go to the semiconductor roadmap, and it tells you exactly where this integrated circuit technology is going to be 5, 10, 15 years into the future. And if you think about folks who are in electronic materials, electrical engineering, and thinking about integrated circuits, doing research on them, the vast majority are working on scientific problems around that scaling. And that's a very valid set of problems to be thinking about, because this is a $1 trillion global industry, and there's a lot of interesting fundamental science problems in the service of that enormous market and enormous impact. It's not the future, though, that we're thinking about these days. We're trying to do something a little bit different and complementary, not competitive with that future, but something that might open up range of opportunities that are currently unavailable, because one thing that has not changed over the years is the platform for all of this electronics. It's always been silicon wafer, which is a wonderful class of material in a wafer form. It's a wonderful type of substrate, but it has certain geometrical and mechanical constraints that make it tough to, say, take your iPhone and wrap it onto your brain, or melt it into your skin, or envelop your heart with it, because the wafer is rigid and brittle and planar. And that's fine for lots of applications, but there are some that require intimate integration with biology that cannot be addressed with commercial integrated circuits that exist today. And the idea is, if you could do some of this stuff, bring all of this power to bear on problems of human health or brain-machine interfaces, that could lead to another qualitative shift in the way that the technology is used, and expand out some opportunities there. So that's a 30,000-foot view of what we're trying to do. Let me pound that message home a little bit further in the context of the brain. And we've done a lot on the brain, the heart. I'll focus this talk on the skin, but the brain is a good illustration to further help me make the point that I'm trying to make. So if you think about the brain, it is a very sophisticated electrical system. And if you want to do therapy on the brain, you want to diagnose abnormality in the brain, or you want to establish a brain-machine interface, the best way to do that might be to take the most sophisticated man-made electronic system, which is silicon CMOS electronics, and interface it with the brain. But that's not easy to do for the reasons I just told you. The wafer itself is planar. It's huge geometry mismatch. What is not quite as obvious is there's also an enormous mechanics mismatch, because silicon is a very stiff, hard material. It has a modulus of about 150 gigapascal. The brain is a soft, squishy piece of jello. Its modulus is about 5 kilopascal. So you have geometry and mechanics problems there. So what do people do today? This is the workhorse. Last 20 years, it's really a pretty nice piece of technology, and it's been very useful for a variety of neuroscience studies. And it accommodates that geometry mismatch through a micro-machined array of doped silicon pins that penetrate down into the tissue on one side, and on the other side terminate on a flat platform where you can mount a chip that you would dice out of the wafer and establish the electrical interconnect that way. And you take that integrated thing, and with an air hammer you mount it onto the surface of the brain. These different pins can penetrate to different depths in the brain, and thereby solving the geometry mismatch problem. But you damage the brain upon insertion. And then what's worse is that over time, the interface between these hard shafts of silicon and this soft jello degrade, because the brain is not static in a mechanical sense. It's swelling, deswelling, it's rattling around in the skull slightly, and now you have a pin in a moving bowl of jello, and that's a bad mechanics interface to think about. So this is great. It will likely remain in widespread use, but what we're thinking about is, what could you do to enable a future in which the electronics are configured to match biology? So soft in a mechanics sense, shape conformal, and then made out of biocompatible materials. So that's a pretty clear example. The heart as well, where you kind of can appreciate the motivation. But the same constraints and considerations apply to skin as well, because the skin, although not as soft as the brain and not as reticulated in geometry as the brain, is rough and stretchy and flexible. And so what's done today usually involves point contact with conductive coupling gels, tapes, individual wires that run to a separate box of electronics. So electronics really not integrated with the skin. It's electrodes. And this is great for a hospital or research environment, but nobody's going to wear that long term because you got wires running all over the place. And then also this tape interface to the skin is irritating over time for reasons that I'll get into in a few moments. So not great for long-term wearability. Also not great for improving the sophistication of the interface because as you add electrodes, you add wires, and pretty soon you're swamped with wires, and it becomes a difficult scaling, which is a shame because the electronics themselves are racing ahead according to Moore's law, but then your interface to the body is stuck in this kind of old approach. You can get better, and there are commercial devices and more sophisticated than this, obviously. And this is kind of one example where you have bare die or individual chips mounted onto flex PCB. So a tape of polyimide, you have adhesive on that, and you can put it on the forehead in this example. But still, it's not great. For the same reasons I just mentioned, you eliminate some of the wires, but you don't eliminate the mechanics problems at the interface, which are driven by the fact that the skin is soft and stretchy, and even a tape is only flexible. It does not stretch. So it's constraining the natural motions of the skin, and that's kind of a problem. So if you think about that set of circumstances, you might conclude, I got to use something other than silicon if I want to do better. And we've been working in this space almost 20 years by now, and we spent a lot of time looking at alternatives. And the semiconductor is probably the most challenging materials component of an integrated circuit. And so you can think about organics, so polymers, small molecules, single crystals, maybe carbon nanotubes. I don't think graphene is interesting. Tubes, let's say these classes of materials. You might say, okay, polymer would be a good choice for a semiconductor because it's already kind of soft, it's bendable, whatnot. We spent a lot of time on this. We built flexible displays like this one in the early days. The problems with polymers are that their electrical properties are lousy. So you can do a slow, non-emissive display like this. You want to do a liquid crystal display, that's a lot tougher. If you want to make a high functional interface to the brain, that's out of the question. So the topic might be then, I need to synthesize new polymers so I can move this metric for transistor performance in terms of the mobility in centimeters squared per volt second from this regime up to something more comparable to state-of-the-art inorganic electronics. But that's a large number of, that's orders of magnitude is the point. And so you got a huge gap. How you're going to span that gap becomes a topic of research, and a lot of folks are still working on that. We sort of moved away because that just seemed a little bit too daunting. And instead, come back and ask the question, is silicon really ill-suited for this kind of thing? Certainly in the wafer format it is, and certainly the intrinsic material properties are not well matched, but could you do some simple things to effectively bypass those apparent limitations? And that's where we focus, and that's what I'll talk to you about today, but not in a super deep level, just give you a sense of it so I can skip over to what kind of devices are enabled. So if you think about the wafer, as I already mentioned, and as you know, you can't bend it. And if you try to bend it, it will crack very quickly. Why is that? That's because partly the material properties. So if you think about the bending stiffness and the degree of bendability is defined by the peak strains associated with bending to a given radius of curvature. It depends on the intrinsic elastic properties of the material. That's the Young's modulus, and you're stuck with that if you want to go with silicon. But it scales with thickness in a pretty straightforward, easy to understand way. It was a really strong scaling. So the bending rigidity or the flexural rigidity, bending stiffness is the product of these two things. So what that means is if you think about plotting the bending stiffness as a function of thickness in a log-log plot, you have a power law behavior. So for a wafer that might be a millimeter thick, the bending stiffness is maybe 10 Newton meters. But if you take that wafer, you shave it down to something that's sort of nanoscale in thickness, so this is 20 nanometers in thickness, you've reduced the bending stiffness by up to 15 orders of magnitude. So now it's 10 femtonewton meters. And although that's just linear elasticity, Newtonian mechanics, there's nothing quantum about that. Whenever you change a material property by 15 orders of magnitude, that changes qualitatively the way you sort of think about it. And in fact, silicon with that thickness is floppy, very, very flexible, as illustrated with this SEM image, in the sense of a low bending stiffness, is also in sense of degree of bendability. So the peak strains associated with bending are going to define how far you can bend it before you crack it, because silicon can only withstand about a 1% tensile strain. And what you see is for a given bend radius R, that bending strain goes down linearly with thickness. So not quite as strong a scaling as the bending stiffness, but nevertheless, thinner is better. So very flexible, very floppy. Now, if you think about a silicon sheet with that type of thickness, it's great, it's bendable, but it's incredibly fragile. You touch it, it'll shatter. It's just not a sensible platform for an integrated circuit in the same way that a silicon wafer is. And in fact, that's why people use wafers that are this thick. It gives it some robustness so robots can move it around and you can put it on a PCB, for example. So, next question is, maybe you think about this as a building block material for an integrated circuit you'd build on a sheet of plastic or a piece of rubber. And so that brings up the next challenge then, which is how do you go about gluing a piece of silicon to a piece of silicone rubber? And that's a hard problem because the material properties are so different. The thermal expansion coefficients in particular are very different, 100 or 1,000 times different. And as a result, it's hard to come up with an adhesive that would keep a silicon chip bonded to a piece of rubber in kind of a realistic way. But there again, thickness comes to your rescue, because if you think about what drives interface cracks, it's this parameter, which is the energy release rate. And you can see how it depends on the differences in thermal expansion coefficients of the two materials. Also, the change in temperature is driving interface stresses. But here again, it's scaling in a nice way with thickness, which means that as I decrease the thickness of my silicon, the energy release rate goes down, the propensity for a crack to open up is diminished. And so it relaxes a lot of constraints on what kind of adhesives you need to think about in order to keep these dissimilar materials bonded together. Here's an example. So this is a very thin plate of silicon. We've printed it down onto a micro-machined ridge on a plastic sheet. There's no adhesive at all right here. This is just van der Waals forces keeping it in this cantilevered state, partly because of that scaling. So thin silicon is what we like. It's floppy, it's very flexible, and it's sticky in some sense. So you can do this kind of heterogeneous integration. So those are nice features. Thin silicon looks pretty good, but not good enough, because this kind of characteristic is not what you want or you need if you want to get on the human body. So this is bending. What you really need is something that can both bend and also stretch, because if you only have bendability, then you can only wrap cylinders and cones. You can't even wrap a sphere, much less a brain or a heart. And you can't accommodate the kind of complex motions that organs are undergoing all the time either. So you need stretching. And there's no thickness to which you can make the silicon that will impart stretchability. So that may seem like a daunting problem, but even that one is really easy to overcome, it turns out. So if you take this thin silicon and you bond it to your elastomer substrate, ultimately you want something that stretches, you probably need to use a stretchy substrate. So you stretch out your silicone rubber, and then you use surface chemistry such that upon contact, this silicon will bond very well at the interface with the rubber, such that when you relax the pre-strain, it induces compressive forces on the silicon. And what happens, it will cause the silicon to spontaneously buckle into that type of shape. And that's pretty nice, because it's an accordion bellows made out of silicon on silicone. And in particular, if I stretch it out now, I'm not stretching the silicon itself, but I get it effective end-to-end stretchability, because I'm trading out-of-plane displacement for in-plane deformation. So the amplitude goes down, wavelength goes up as I stretch it out, and then the reverse happens when I compress it back down. So that's simple, and it works, provided you understand what's going on with the mechanics, because this kind of thing is a hard-soft composite. You have to know where the stresses and strains are if you want to do real engineering with these kind of ideas. And we spend a lot of time on the mechanics, where entire papers just on that type of structure, so we understand what's going on. So that's the idea. Thin silicon, buckling physics, off you go. You can make integrated circuits. This is not an integrated circuit, obviously. It's just a test structure. And it's not even a good starting point for an integrated circuit because you're never going to do device processing on rubber. It's just not going to happen. But you can make ultra-thin circuits, fully formed, flexible, and then as a back-end packaging step, you bond them to this pre-strained rubber. You create all this buccal, wavy shape. Now you have a composite that has the soft mechanics you want. And this is an example of one of these stretchy integrated circuits based on silicon. This is a picture taken at our Beckman Institute. We have an imaging technologies group, and so they made a nice image here. So this is a glass pipette. They're just pushing down on the center of our circuit, and you can see how it is able to deform in a continuous curvilinear way. You can see the different wrinkles in the interconnect traces, and here you can see that particular trace is stretched out by this local force. So all the wavy structure that was originally present has been pulled out. You've pulled your accordion all the way out to its full extension. If you kept pressing, you'd probably crack that line. So the key is be able to understand what is the range of deformation that your devices can accommodate and do the design up front so that your application requirements can be satisfied. So circuit design combined with mechanics design to allow you to do what you want to do. Now the key thing is that you haven't sacrificed any of the electronic properties by doing all this stuff. So it's thin silicon, it's wavy circuits, but the electronic performance is very much comparable to what you see in a wafer-based system, factor of 1,000 better than what you can do with the organics. Very nice switching characteristics in both types of transistors, and this is just a simple ring oscillator. So you've taken this stuff, you've crumpled it up, and yet you've done it in a systematic way with understanding the mechanics, so you haven't disrupted the electronic function, and that's the key part of this, obviously. Yeah?
Do those electrical properties stay constant when the material is under mechanical load?
Yeah, so that's a good question. In this geometry, no. So there's actually finite strains at the device positions. This is a P-channel, N-channel MOSFET, and it's a ring oscillator. Mobility, or the switching characteristics of the transistors change slightly with strain. That's been exploited by the semiconductor industry to increase the speed of integrated circuits. At a modest level, I would say, kind of a 20% type shift in the output currents. So in some cases you can live with that. In some cases you cannot. And in cases that you cannot, you actually take this circuit and you can do things to it to strain isolate the active devices to eliminate that dependence. But it's coupled in this very simple implementation. But I won't step you through it. The basic idea is thin materials, hybrid hard soft composites, and buckling. And from there, all kind of elaborations and different things that you can do to accomplish strain isolation. It's a very good question, but you can sidestep. It's an engineering problem. So if you can make soft circuits that way, then what do you want to do with it? And I outlined at the beginning what we have in mind, and that's putting things on the body. And it could be inside the body, could be on the body. We got interested in skin-mounted maybe 4 years ago, I guess, and started to think about what's out there today that goes on the skin, unlike these tape-on electrode wires, that is comfortable and works. And we thought about kids' temporary tattoos as maybe a model to think about how to do circuits on the skin, because they look great. You put them on your skin, you move your skin around, it can kind of wrinkle, stretch, deform with the skin, and you don't even know it's there. So that's what we set out to do, is to think about whether we can make an integrated circuit and sensor suite that has that kind of mechanics or something as close as possible to that. And what does that mean? That means as thin as you can go. We had a target of 5 microns. We got pretty close to that regime. As light as possible in an areal mass loading sense, so maybe a milligram per centimeter squared. As low in modulus as you can go. We had targeted something kind of brain modulus level, 5 kilopascal, but the skin is actually much stiffer. It's about 100 kilopascal, so 100 would be good. We a little aggressive on that, but 5 kilopascal. It needed to be at least as stretchable as the skin itself. So skin will stretch to about 30% before it starts to tear. So we want something that would have that kind of elastic level stretchability. And then some additional requirements. You need your sensors and electronics electrically isolated from the skin, so it needs to be waterproofed, but at the same time you don't want to disrupt natural processes of transepidermal water loss, so you need some level of permeability as well. And so that's what we had hoped to do, and there are a lot of challenges in getting anything on the skin, and they relate to issues in long-term viability in the interface, and you got to have access. Adhesion is always a challenge. You want something that's soft and conformal, like a tattoo, and then cost, power, weight, and size also relevant considerations. This one is a big one, and has been over the years. How do you do robust bonding or binding without irritation? And it turns out that problem is directly related to the mechanics goals as well. So I'm not going to go through all the details. Let me just highlight the key points. So if you think about modeling the mechanics of a piece of electronics, just a generic material bonded to the skin, you can run different scenarios in terms of the modulus of the electronics and its thickness. And you can calculate interface stresses in particular that tend to drive delamination. Those could be shear stresses or peeling stresses, and you can do it for different scenarios. Silicon chip glued to the skin, flexible electronics, so plastic sheet on the skin, thinner, lower in modulus, or all the way to this kind of tattoo-like construct that I put forward in the previous slide. And what you see in both cases, peeling and shear, is that the stresses peak up at the edges. So if I stretch on the skin, delamination will start at the edge, which is sort of intuitive. But then look at the magnitude. So the magnitude for otherwise similar level of deformation for the silicon chip is large, smaller for plastic sheet, and then smaller still for this skin-like. Same thing over here. But the actual magnitudes are what are notable here. So if you think about the ratios of the stress, silicon chip to plastic sheet for skin in tension or under a bending deformation, going from silicon chip to plastic sheet helps because it's reducing interface stresses, but not by a huge amount, by about a factor of 4 to 5. Now, if you think about the ratios, though, for silicon chip to this electronic skin, this skin-like scenario, now you're talking about 5 orders of magnitude. And that really changes the way that you think about adhesives to the skin, to the point that you don't even need adhesives at all. These things just cling to the skin because they're so soft and deformable. And so you can see that. It's easy to do that experiment just to see the consequence of that mechanics. So this is same chemistry in an elastomer, a silicone-based material. All we've done is we've changed the density of crosslinks between polymers in this material to change its modulus. Same thickness, same interface chemistry, just different modulus. And you can laminate it onto the skin. It's sort of near the wrist. And then you can flex your wrist and you can see what happens. No adhesive. This is just a tackiness of the material itself keeping it bonded. So here's a silicone material with a modulus of about 1 megapascal. So you flex your wrist and it delaminates. You stretch the skin. Again, it drives a delamination front that begins at the edge. Now if you do the same exact experiment now with, let me see, can I get rid of this? Now with lower modulus, here's what happens. So same thing, same region of the skin, same interface chemistry, same adhesive strength. It doesn't delaminate. And that's just because you've minimized the interface stresses. And it sticks now, it just clings, and you can move your wrist around and it stays put. So that's the basic.
Sorry, what was the change between the first and the second?
Modulus, stiffness.
Just the modulus.
Just softer, yeah.
What about isolated clusters of microneedles or nanoneedles to give you a
You could do that, yeah, penetrating pins. Those are options. We were trying to get the thing stuck on the skin without any straps or pins or tapes. But you could add that to improve the robustness of the adhesion. You could definitely do that. So how do you get something that has very low modulus? So I told you some tricks to get stretching. But now you need stretching, but also a very low stiffness, effective stiffness. And it's a tricky problem. You want a device that has a modulus of, say, 100 kilopascals, but you want silicon in there, and that modulus is 150 gigapascals. So how do you do this kind of composite engineering? And this is one way to do it. So illuminated by full 3D finite element modeling. So you take a circuit, ultra thin one like I mentioned before with silicon nanomembranes, but don't use it in the form of a continuous sheet. Cut it into an open spiderweb mesh like this in terms of these intersecting filamentary serpentine wires and devices built into that. And then bond it to a low modulus silicone substrate, thin, 30 microns in thickness, 50 kilopascal. If you do that, fully optimized with modeling guidance, and then you stretch it along this direction or along this direction, you can measure stress-strain behaviors, and that's telling you how stiff it is. So the first thing you see is that the measurements along X and Y are quantitatively captured by the modeling. The other thing you see is that the modulus is very much comparable to the epidermis itself, which has a modulus, that slope is about 160 kilopascal, and you can see it starts to go nonlinear around 15 to 20% strain. So this is actually a better material in some ways. You can stretch it further, but in this small strain regime, it's very well aligned with skin itself. So that's a framework into which you can drop transistors, integrated circuits, sensors, and so on. And so this example of a field effect transistor, there's a resistive trace of silicon, very thin silicon cut into that geometry. Here's what it looks like. The transistor performs well even though it's in this funky configuration. You can do sensors, these are strain gauges, you can do photodetectors, other kinds of things. We've done many classes of devices in this context. So here's what it looks like when it's mounted up onto the skin. Very soft, no penetrating pins, no adhesive, you just laminate it on. Good to go. Same kind of experiment. This is laminated on the skin of the postdoc who did the work, and then we poked them with a glass rod so you can kind of see how that moves around. If you grab it at an edge, you can peel it off. This is what it looks like. It's so flexible and floppy and soft, it doesn't even support its own weight. It just kind of collapses down onto itself to give you a sense of the mechanics. You know, the practical, yeah.
So when you're making those, you're spin coating, I assume, silicone over PMMA. Is that the substrate?
Yeah, so these filaments are polyimide, and then in certain regions there's silicon and metals and dielectrics to make the devices.
You're taking that substrate, probably doing it on a wafer, pulling it off.
Exactly,
and then,
yeah, exactly. And then transferring it to the soft substrate. And the key there is to keep the elastomer out of any kind of processing. It's not going to happen because it moves around too much. You can't get registration from layer to layer. Yeah, yeah, good question. So in terms of this mechanics, you know, the practical question is how do you hold this stuff and, you know, manipulate it around? And, you know, there we just use water-soluble tape. Okay, so PVA, put the circuit on there, flip it over, put it on the skin, wash away the tape, and that constitutes the mounting procedure. So I have a movie to show that. So this is it's just a demonstration platform that has a number of different types of active devices, transistors, diodes, inductors, capacitors, LC oscillators, temperature gauges, strain gauges. There's an inductive coil and then an antenna that runs around the outside. So what you're seeing is this transparent tape backing, allowing the student to place this circuit directly into contact with the skin. So it's skin, circuit, silicone rubber backing, and then that PVA tape. And he's washing away the tape by applying a little bit of water. And eventually that will disappear and just leave the circuit right here behind and the circuit substrate, which extends a bit further out around the periphery here. And you'll kind of see that. So once it's gone, then it's just this epidermal electronics on the skin. And you can see then by pinching the skin, you can get a sense of what the mechanics is all about. So here's just the silicone rubber backing. Here is the rubber backing plus the circuit demonstrator. And as you pinch this thing, what you see is that the skin wrinkles and folds and deforms in the region where the circuit is located, almost exactly the same as the way it deforms in regions where the circuit is not located. So that's sort of validating the design approach. So the circuit is not constraining the skin or preventing it from behaving in a natural way. And as a result, you put these things on and you don't even know that they're there. And that's with no adhesive. So you can squeeze it, move it around. The interface is strong enough to stay bonded, but not in an absolute sense. It's not strong bonding. So you can just grab it at an edge and you can peel it off. And that's what you're seeing. That's what you're seeing here. Yeah, so there are a couple of ways to do that. You can come in with one of these water-soluble tapes, stick it there, and then peel it off. It'll come with the tape, and then you can do the mounting again. But in this case, you could not reuse that, let's say. So, the absolute strength of the bonding is not great, but if you want to do better, one way is to just use, existing temporary transfer tattoos as substrate. You already have the FDA-approved glue, mount it on the back, and then go through the regular thing. So this is an Illini pirate, just somehow pirates and tattoos. There's no ocean anywhere near Illinois, so this doesn't make a lot of sense, but in the context of tattoos, maybe. So you flip it off. Now, the additional benefit of this is you can conceal your electronics, so if you're into covert things, and we've worked with CIA and so on, that turns out to be a relevant capability. So the circuit is kind of right there in the facial region of the pirate. So I used to travel around with these circuits mounted on my skin just so people could see it, but requires students to make lots of circuits. So I don't do that anymore. I've given them a break.
That's the integrity of the circuit.
Yeah, so you can. I'll come back to that in a second. There is a finite time over which you can stay on the skin and remain viable in terms of function. I'll describe that in a second, but I'll just, instead of wearing them, I just carry some representative examples around. So this one is one of these kinds of circuits, but embedded in about a millimeter thick sheet of rubber. So this is not epidermal, but you can handle it and kind of twist it around and get a sense of what's going on. The other one is one of these epidermal constructs on PVA. So the mechanics here is dominated by the tape, but just to give you a sense of what it looks like. Just pass those around. So to your point, how do you get these things on and how long do they stay on? So tattoo is not bad. This just van der Waals forces, it's okay for an office environment, but if you go swimming, it's coming off, And so how do you get it to stay on better is something that we started to think about. And what we found is that a really simple way to get very robust integration with the skin that does not compromise this epidermal construction is just use spray-on bandage. So I don't know if you guys have ever used it. Go to Walgreens, you get a little spray can of this stuff. It's a copolymer of an acrylate and a silicone. And you can spray it down as an adhesive, and then you can spray it down on top as an encapsulant. And in that case, you can print just the circuit, so no silicone backing at all, just the circuit, printed off of a silicone stamp. And that's what's shown in this video. It's a little more advanced way. So there's the spray-on bandage. It's a few squirts. That's only about micron thick sheet of that spray-on bandage material, but it's a nice adhesive. You print your circuit right onto your skin like that, and then you spritz it up with some more spray-on bandage on top, and you let that dry. And now it's much thinner than it used to be, and it's also much more robust from a mechanical standpoint. So there's a video we have of, so now you can go swimming, you can take showers, you can exercise, you can do essentially whatever you want. And it won't come off. Typically, after a few days, in the morning, you add a little spray-on bandage to, maintain the integrity of the encapsulating layer. But, just give you a sense, it's a little bit bigger. It's a piece of electronics designed to do something a little bit different than what I showed you before. This is actually a functional thing, and you can wash it and do your thing. So, time frame. These devices will stay on about 2 weeks. That's about it. And it fails not because of a deficiency in the adhesive or the encapsulating layer. It fails because the skin is exfoliating cells from the stratum corneum all the time. And the time scale for that exfoliation is about 2 weeks. The entire surface of your skin is gone kind of in that time scale. And so you're not sitting on a stable platform. It's shedding, those cells and your circuit with it. So that's a fundamental biological process. I don't see a great way around that. You can imagine taking the device off maybe for a day and then you could reapply it or something like that. But that's just the practical reality of where these things are. So this is what it looks like on the skin. This is spider web stuff, and the key thing is that it's conformal to all of the very challenging topography of the skin except the most daunting crevices. And that's good from a standpoint of adhesion, but it's also good in terms of the interface to the skin. So the skin is a window into health and wellness and physiology of a person wearing the device. You can imagine, put a cell phone in this format. I think it's more compelling to think about applications in wellness and sports and healthcare. So that's where our emphasis has been, and this kind of contact ensures that you can make good measurements. And you can make those measurements on any place in the skin, like places where you would not be able, in a practical sense, to have a wire and a piece of tape. So finger, back of the neck, forearm, jaw. So if you come into the group, you have to be willing to do this kind of thing. And then you can make all kinds of measurements. I'll come back to the details of what these measurements are, but there are a number of different measurement options that we've shown. And one of them involves just measuring electrical activity associated with muscle contractions, either the heart or the skeletal muscles or muscles that are controlling your eyes or your throat. I'll show you speech, and I'll show you examples of all of those. This is the heart, so you can measure EKG with high fidelity, and the detailed waveform there is saying something about health status. If you put it on the chest, if you put it on the leg, you can measure EMG, that's electrical activity associated with contraction of the skeletal muscles. You can measure things related to gait, for example, so the subject is walking and then standing. This is that epidermal electronics here. Here's the conventional paste-on electrode with conductive gel, just to do a comparison. So we're not claiming that the fidelity of the measurement itself is higher, it's comparable, but it's different because you don't have a piece of tape, you have something matched to the skin, and you don't have just an electrode, you have full electronics. So it's really a lot different, but the fidelity is about the same. Yeah.
So was there circuitry on the device that was actually filtering or amplifying or doing anything with the signal?
Not in this particular case. It was just a dumb electrode interface. Yeah. You can do that, and we have done that, but not in this particular example. Yeah.
Get the wire off of that dumb electrode.
I'll come back to that in a second. Very good question. If you put them on the forehead, you can measure EEG, and you can see all the standard things. You do Stroop tests, and you can look at alpha rhythms. And so if you put on the head, you might think about a brain-machine interface, but these devices, because they can go on unusual parts of the body, you don't have to think just about brain-machine, but just more generically human-machine. And we found that if you put these devices on the throat area, then you could pick up complex patterns in EMG associated with muscle contractions involved in speech. So if you look at the spectrogram of data that you collect when the subject is saying different words, either vocally or subvocally, you can see different patterns. And we work with folks in electrical engineering to do pattern recognition. So you can train the system on a finite vocabulary of words and then use that as a brain-machine interface. Maybe for somebody who suffers a disease of the trachea or as a prosthetic control mechanism. My students wanted to develop like a game interface. So this was a very simple example. This is a couple years back, but you could just move a cursor up, down, left, or right. I've never played this. It's some kind of strategy game, but just with your neck. So if you want to play a video game with your neck, we have the technology for that. So maybe interesting, maybe not that compelling. But anyway, it's a demo. We got a little bit better over the last year and a half or so that things can happen faster in terms of the interface, so it doesn't have to be just strategy. A game can be more of a action game. And there are companies out there now trying to do things like this. The hardware is totally different, but let me just show you that you can do this by EMG control. So this is a helicopter drone. Actually, if you just turn out the lights momentarily, then this movie shows up a little bit better, and then we can go back to lights on. So this is a postdoc over here, so it's bimanual control. He has these epidermal electronic patches on both forearms, and then there's a computer system that takes that data and then translates it into a set of commands for the helicopter, and you can see that go here. So the helicopter, he'll rotate his fists, and the drone takes off, and then he's tilting his fist this way. It rotates in that direction. He'll stop that. It will cease rotating. Then he clenches his fists, and it will fly off in that direction. Release. Rotate the other direction. It will land. Then he'll rotate again. It will take off. And he'll tilt back the other direction, and it will rotate counterclockwise in this case. Stop, then clench his fists, and he's trying to fly the helicopter back to get it to land in that box, and he'll cause it to land, and you can see he missed. So needs a little bit more practice, but you get the idea. It's just a demo, academic level demo. But we think that these devices could be useful in a more commercial setting, and for that reason, 2-3 years ago, we put in place a startup company in the Cambridge area, and they're trying to push these kinds of ideas out more into the real world. And they're interested, as one application area, sports, wellness monitoring, and as an example of a sporting event, to the extent you think about NASCAR as a sporting event, we put devices on this guy's really interesting guy, undergrad at Duke, so he's a really young driver on the circuit, but he's interested in advanced technologies. So we put these things on, and he races. We've been in it 2 or 3 times now, and it's a great proving ground for the technology because it's incredibly hot in these cars, a lot of sweating, and it's an endurance type of thing. So that's been a great interaction. We also have, as head of the sports segment at MC10, former NFL guy, Isaiah Kazvinsky. He's the highest draft pick ever out of Harvard. He played for Seattle Seahawks, actually, for 8 years. Played in the Super Bowl in 2006, and he's assembled a sports advisory board. So usually in a small company you have a technical advisory board. We have that, but then we have this other really cool thing, sports advisory board, and you got all these famous guys who are part of that, and providing input on like what kind of function you would want. It's not just lending their name, but actually really intellectual input to what MC10 is trying to do, which is pretty cool. So MC10 makes these kind of patches now, here, and they launched their first product in July. July 3rd was the launch date. It's a joint offering with Reebok, and it's a piece of flexible electronics that goes in sort of the brim region of a soft good, a skull cap, that measures in a very precise way 3-axis accelerometry and rotations. So it can quantify the detailed physics associated with an impact to the head, and then it uses advanced algorithms to take that data and then bin it into 3 categories: moderate hit, severe hit, and then a hit that could represent a concussive impact to the head. And the idea is to provide additional information to folks on the field to determine a path of action after a hit to the head. And Matt Hasselbeck, who used to be a starting quarterback for the Seahawks, then the Titans, now he's a backup for the Indianapolis Colts, has been a real evangelist. So this was kind of publicly announced at CES in January. That's Matt with a device on, and then there's our device right there. So that was pretty cool. You got it on the throwing arm of a starting NFL quarterback. Was kind of a nice milestone. But this is a check light. You can order them up if you want one. You can go to Reebok website and you can buy these. So order early, order often. It's a great piece of technology. This is what it looks like. It's about $130, and it keeps a running tab on the total number of hits in these 3 categories to the head during the course of a season. So it does overall dosimetry, I guess, so to speak, in terms of impacts. And this is the indicator system in the back piece of this. So that's one example. We have a lot of other things going on at MC10. Our focus at my own university group is not, we're interested in sports, but back to sort of healthcare. And the wires and the straps and the tapes and so on are a problem for adults. It's a real severe issue for premature babies that require a lot of monitoring. So this is just Photoshop. We've not put a device on a baby yet, but just this is our vision of a way that this stuff could be useful. And to do this, you need wireless, you need a radio, you need onboard power, our strategy to that, and you need sophisticated sensors as well. Let me talk about sensors a little bit, then I'll talk about interface and radios, wireless approaches. So we were doing this work. We were approached by an expert in skin surface temperature measurement at NIH. And when we were approached, I was thinking at the time, temperature is not that interesting. But it turns out it is. If you have an ability to spatially map temperature and measure it at millikelvin precision. So instead of saying your temperature is 98.6, you can evaluate temperature to 98.653. And what's happening in that last digit tells you a lot about health and wellness and what's going on with the body. But you have to be able to do it with that kind of precision and also have some spatial mapping capability because the surface temperature at that level on the skin is extremely heterogeneous. Here's an example of how they do it now. So these are $250,000 very sensitive IR cameras that are imaging temperature profiles in space and time. And this is a close-up image of a thumb. And what you see are these little dots. So each one of these dots is a black region. That's a little bit cooler than the rest of the thumb. And if you play this is at real time, you can see that that pattern of dots is constantly changing. The pattern, and there's a time scale, so it's like a periodic type of thing. Each one of those black dots corresponds to an individual sweat gland. And it fires, a little bit of sweat comes out, it evaporates, it cools locally. And so that seemed pretty cool to me. Like if you could do that without the expensive hardware of the camera, without all the motion artifacts, so getting the thumb to stay still enough to do this is a challenge, then that might be interesting. The thumb, that's kind of a curiosity, but if you look at full body temperature maps during exercise, you see, at least for me, things are really remarkable. So this is an IR image of an individual on a treadmill, and then the images are manipulated to keep these 4 points fixed. And this is time. So this is average body temperature varying as this person is jogging and then kind of running and then resting. And so if you look at this variation and say, okay, that's kind of interesting. It's not, jumping out at you as something that's high in information content. But if you look at the spatial patterns, and again, with high precision and spatial resolution, then you see some really funny things. So he's walking. He'll start to jog very slowly. At this point, he begins to sweat, and you'll see the overall surface temperature of the skin decrease because of that sweating. And so you'll see the body starts to go dark. You begin to see that. And then as it gets darker and darker, you begin to see an amazing level of texture that begins to build up on the body. And these lightning bolts here, that happens to be associated with vasculature, blood vessels, that are transporting blood from the deep muscle regions up to the skin. And there's a thermal transport associated with that. So those are hot regions. That's not sort of dripping sweat. That's really telling you about blood flow and in turn cardiovascular stress and health associated with exercise. So that seemed interesting. So can you do that kind of thing with this epidermal patch technology? And it turns out that you can. Let me give you a couple examples. Here's one of these devices. So now in this case, not only mass loading, but thermal loading becomes a very important consideration, and that was not on our list of metrics when we started this project. But if you want to put a sensor on the skin, it can't load the natural processes of water loss and sweat, and it can't heat as a result. So that becomes an important aspect, and we spend a lot of time on that. But you can use the high-end cameras at NIH. You can measure this way, and then you can measure that way, and you can look at the precision and the accuracy in this kind of sensor. And it turns out that without a huge amount of difficulty, you can do this. So here's temperature as a function of time, measure with the IR camera and one of these epidermal sensors, just offset for clarity. So what you see is that when the patient is just at rest, there's some periodic variations. This is associated with natural vasoconstriction, vasodilation of blood vessels in the near surface region of the skin. There's characteristic amplitude and frequency associated with that, which itself is interesting, but the purpose of this graph is to show you what happens and the kind of subtle things you can pick up. So here, at this time, the patient was told to do a series of operations in mental mass, so division and subtraction. And what you see is you can pick that up, the effects of that, because now your skin is sweating a little bit. And so you can see that cooling. So you can say something about cognitive state. The other thing that you can do is you can really pick up subtle effects of physical activity. So here we are again, sensor, IR camera, rest, now physical stimulus, now rest. So in principle, you see the same kind of trend I showed you with the treadmill temperature goes down, then it stabilizes. But this physical stimulus is very subtle. So you have one device measuring on the left palm, and the physical stimulus corresponds to rubbing two fingers together on the right hand. So just to give you a sense of the precision and the kind of coupled response of the body is sort of interesting to me. So I'm running out of time here, so let me just skip through and get to the last few slides. So there's a question about Interphase IO. So what we've done is things in two parallel tracks. One is, let's use a soft cable like this, hardwired connection, just so we can understand how the sensors are behaving. We do the thermal mapping, we do EEG, we can do other things. And we can also look at device lifetime. So here's EMG, we're measuring on the forearm right after the device is mounted, and then a week later, where the subject is doing showers and all the normal stuff, you come back and it's pretty good. Maybe a little bit of increase of noise, but not too bad. So here, this is a releasable cable. We laminate it on, make the measurement, we peel it back, then off they go. That is not the vision, though, of how this technology could best be used. You'd like to do wireless interfaces. One way to do that is a simple passive wireless coupling, mutual inductive coupling between an external coil and a stretchy epidermal coil that's coupled electrically to the skin. This is one way to do it. You can measure thermal conductivity of the skin. You can measure hydration state, impedance of the skin. You can do different things in that way. And that's fine for certain applications. It's not completely generic, however. And so I'll show you at this point some things that's still unpublished, but it's the result of integration of a full active radio on the patch. And so I won't get into details, but this is full wireless radio transmission of EEG. The green traces are traces measured with the epidermal patch, the blue with a standard wired based system. And you see a good correlation there. Here's ECG in a sitting state. Again, very nice correlation between epidermal and standard wired approaches. This is EMG, same thing. Waveforms look a little bit different here, but again, this is ongoing work, so we're trying to tease out the details here. This is measuring EOG, so you can put these things near your eye, and you can track eye motions because there's muscle activity associated with that. So this is moving the eyes up and down. You can see conventional EEG, and then this is horizontal back and forth motions of the eye. And we've shown, and this is not great, I can't even put a movie in here, but you can do game control with that kind of thing. Eye motion, track using an electrical measurement and a wireless link. And we did Pac-Man, but I just have a still image here. So that's kind of all I wanted to say. I would say, what we're trying to do is still early days. There's still lots of opportunities for, as I was saying before, new ideas or advanced technology development. But I feel like we have some ideas in place and some functionality that's headed in the right direction, I guess I'd say. It involves a lot of collaborators. Yonggang Huang does all the mechanics theory. Placid Frere does the manufacturing systems. Todd Coleman, we've worked a lot on EEG. These two guys on brain-machine interfaces at Beckman. But ultimately, the students do all the work. They come up with a lot of the best ideas. And so it's best to kind of end the talk by acknowledging them and thanking you for your attention. I'd be happy to answer questions if you have any. Yeah.
So maybe the power is also inductive in the sense how the circuits are powered, so not only for taking the signal out. And do you have enough storage built into them?
Yeah. So those are great questions. So the answer is yes to everything. So you can do inductive. You can do far field RF power transfer. We've done both of those. This is an example of inductive powering of LEDs. These are for implantable devices. You can get them subdermal and you can light them up in that way. I don't have our far field RF transmission data, but you can do that as well. There's a fair amount of RF comes out of your phone, and so you can harvest even a small fraction of that. You can begin to do things depending on the power requirements.
What kind of power requirements do you have?
So for our radios, so we have a multifunctional system that does EMG, temperature, and accelerometry with a voltage-controlled oscillator for the radio frequency communication, about 2 milliwatts. it's low duty cycle. But that's not very sophisticated. I mean, think low power, Bluetooth, sub-threshold logic. There's a lot of opportunities for driving down the power requirements. But if it's a couple of milliwatts, you got a watt coming out of your phone, you're pretty close to something that's reasonable. I think in the case of a confined environment like a hospital or a research lab, you can always put an RF source, a patch antenna in one corner of the room and do it that way. And in fact, we haven't done that in a continuous mode on humans, but we have done it for LEDs injected into animals for optogenetics studies at Washington University. So that's full wireless power and controlling when the LED is coming on and off. So inductive far field RF are two options. In some of these passive systems, you don't need power directly on the device. The other, would be storage, right? A battery. And I think batteries are possible. Batteries, I just be cautious. I think batteries are challenging. So we're working on it. I think you can do it. There's some practical aspects around how do you achieve robust encapsulation when you're in a soft rubber situation. And I would say that that's a challenge maybe for the community. It's not one that we've solved. We're still thinking about it. But we can do batteries that are soft and stretchy, and this is an example of one. So this is a rechargeable lithium-ion battery. Not a huge capacity, but you can run an LED. And the way that we make it stretchable is basically just take conventional lithium-ion anode and cathode materials and create very small cells and then connect them with the deformable wires and then package it soft elastomer top and bottom and an electrolyte gel in between. And so you can do that. So this offers extreme wide range of stretchability, maybe up to 400% biaxial, as you'll see here. And it's, the LED stays on during this deformation. So, so not out of the question. I personally prefer a far field RF because then you just need an antenna. It's very simple. It's constraining a little bit, but again, I keep thinking about the smartphone and you might be able to use its battery essentially, right? And ultimately the phone is going to be a part of any kind of monitoring system anyway. So, so yeah, power is a good question. We also do mechanical energy harvesting, so you can do piezoelectric materials. We've done a lot of things on the heart. Heart's moving. You can generate enough to power a pacemaker, but for things that are on the skin, you have to think about where you're going to put it to get enough continuous power to make sense. And it's not clear to me how that would work, but we're still, we're tinkering around with that. Yeah.
All your examples and your answer to that question assume that everything on the device meets all of your flexibility constraints and all of your air still gets to the skin okay constraints. Is it, if you're willing to sacrifice those constraints for a few millimeters here or there, can this coexist with traditional silicon and traditional like whole ICs or batteries or whatever?
Absolutely. You can think about it. It really depends on the application requirements. So what I didn't show you is we have ways to just take unpackaged bare dye and get it into a format. It's not full epidermal, like the full academic thing that we kind of strive for. But a lot of cases, it's good enough. You talk to our sports advisory board folks, and we hand them the thing that's made with the bare dye type approaches. They look at it and think, fantastic. It's like, it doesn't need to be.
Put something a little bit rigid there because you want that part to not bend because for all the brittleness reasons.
Yeah,
before,
it's
you
all,
just kind of put a little piece of plastic under
it's
it.
all about mechanical engineering, doing things like that. Yeah.
Are you wire bond attaching in those cases, or how are you attaching to the die, bare die? Yeah,
there are a few different ways to do that. Maybe offline, this is being recorded or something. We haven't published that yet. So there are 2-3 different options. So you can imagine what they would be. There's not
that temperature work is really interesting. Have you considered sort of subsurface blood flow?
Yeah, absolutely. So I kind of ran out of time there. So we're doing a lot around core body. I know you guys are too. You can do blood flow, and that's interesting because the precision you can pick up temperature changes, you can see effects of flow on thermal diffusion. So if you put one of these devices on the arm, you constrict the bicep to prevent flow through an ulnar artery down the arm, and then you release that. You can see a thermal effect, essentially a pulse type response associated with flow. And again, you have to be able to do mapping because you don't know, it's hard to locate that artery, it's deep in the tissue, but here's one of these devices. This is while the artery is constricted, and then you release it, that's the artery right there. And you can pick it up. So some of these channels have very little response. They're not overlapped, spatially coincident with the artery, but some have very strong response like that. And this is the IR camera. So again, almost perfect match with that $250,000 piece of equipment. And the details of how far it overshoots here, what the time scale of this is, can be related to the flow properties. And that is an important indicator of cardiovascular health. So you can do this. What we're finding, though, is that you can also do something that doesn't even require the constriction. Like if you put the patches on the arm, the thing that you can do with these patches that you cannot do with an IR camera is you can operate the temperature sensors as heaters. So you can light them up. Here we've heated up these 4 in an array of 16. And blood flow will cause anisotropy in the resulting thermal distribution. So if there's an artery running down in this direction, then heat will tend to spread more this way than that way or that way. And you can map blood flow in that manner. What this slide doesn't show that, but this slide is showing that you can determine thermal conductivity of the skin. So you can pulse the heat here, and depending on how efficient a heat sink you're sitting on, that determines the ultimate temperature of those heaters. And with a simple model, you can back out thermal conductivity. Now, why is thermal conductivity interesting? Is it because it quantitatively correlates to hydration of the skin. And so we use a conventional moisture meter. It's a handheld thing that makes the measurement electrically, but we see a very good correlation there. So you can do temperature and hydration and blood flow with this patch.
Being laid over this.
Yeah, right. Could be multifunction.
Much richer.
Yeah, right. So we can do impedance measurements of the skin, look at galvanic response, things like that. Yeah.
All this is sticking to the skin. Can it stick to other stuff? Internal organs?
Yeah, so I didn't put slides. We've done a lot of work on the heart and the brain. Yeah, and I didn't put it in because it seemed like it was kind of outside of the Microsoft type of realm of interest. It's sort of hardcore clinical medicine is the context there. Yeah.
Power requirements aside, have you guys thought about using these devices for presentation of information as opposed to gathering of information? So you gave the little LED example, but
yeah, LEDs are not great because they're power hogs, and you're trying to minimize power. So we've thought about electrophoretic display elements because they're bistable. You have to think about the mechanics there. We have done some work on thermochromic materials. So, I think Coors beer has like a thermochromic thing. So that kind of material. And it turns out you can embed those dyes into rubber. So you can make a fully stretchable, little simple indicator. And it's being switched by heat. And so if you run the numbers, it's more power efficient than an LED. It's not bistable like electrophoretic ink. So we made a little stretchable indicator using Leuco dyes, these heat sensitive dyes. But there may be some other concepts. That's kind of what we're thinking about. The Reebok device is just LEDs, but I think there's oftentimes value in having the indicator right on the patch. So I think you're asking a great question, and we've thought about it.
Can you play that IR video again, please?
Which one?
Just because it was
The
so
thumb or this one?
Yeah, this one.
Yeah.
I don't have a question related to it.
I can send you a copy of the movie. I should really highlight, this is Alex Gorbach, who's our collaborator at NIH, and he's a world's authority on skin temperature, and he's a great collaborator. So this is his movie. This is not something that we collected.
In terms of cost, I assume this is low cost. Is that true? Is there anything that makes it expensive?
No, I mean, it depends on the devices, like those passive devices. I have one of these little hydration monitors here. This is this is one that uses inductive coupling for the readout. I mean, this is just metal traces. This could be pennies, right? Some of the things that involve, radios, obviously be more expensive. But, I think back to our initial motivation, we're trying to do things that are aligned with conventional electronics, and then just do a few things on the back end. So in terms of rubbers and stuff and mechanics. So our thought is that it might be incrementally more expensive, but it's not going to be qualitatively different in cost structure, but qualitatively different in mechanics and user interface.
Thanks, Tom.
Okay, thanks.